Okay, so good afternoon, everybody. Let me first of all thank the organizers for organizing the workshop and for giving me the opportunity to present these latest results. So today I'm going to try and describe one of the classical, let's say, standard experiment in helium, superfluid helium, so helium-2 counterflows, which are generated thermically and which have no classical analog. But I'm going to try to describe them in a classical way. So as a superposition of two-dimensional wakes and vortex dipoles. I think this, okay. First of all, I would like to also thank my collaborators, so the people with whom I have performed this work. So Giorgio Krusolovic in Nice, Carlo Baring and Andrew Bagley, who's in the audience at Newcastle University, and also for the last few slides, Carlo Casciola in Sapienza in Rome. So here are a few references where the method, which I'm going to briefly illustrate today, is described and some recent results obtained with it. So this is the outlook of my talk. Because given that I'm the first speaker on helium, I'll do a very short introduction, and then I'll go to present the results. So okay, so this is the well-known phase diagram of helium, and so below this second order transition, which is the lambda line, the red line, helium above, it can be described as a Newton fluid, which is an ordinary classical fluid with low viscosity and density. But when you decrease the temperature below T lambda, then helium becomes a superfluid in the sense that the law of classical fluid dynamics seem not to apply. We'll see that there is still some possibility. And according to the two-fluid model, the phenomenological two-fluid model elaborated by Tisa and Landau between the 30s and the 40s, superfluid helium, which is also known as helium-2, can be described as an intimate mixture of two fluid components, two unseparable fluid components. So the superfluid component, which is loosely related to the condensate, and so to the phenomenon of Bose-Einstein condensation, and the normal fluid, which is a gasothermal excitation, phonons and protons, but in the temperature range we are interested in would be mainly protons. So the fact that we have two fluids and that they are inseparable means that instantaneously in each point we can have two different motions, each with its own velocity field and its own density field. The superfluid component, because it's related to Bose-Einstein condensation, can't carry entropy, and it's also inviscid, while this is not the case for the normal fluid, even if its viscosity is very low. And so, more or less, in first approximation, the superfluid can be considered like an ideal Euler fluid, while the normal fluid is almost, also in first approximation, can be described as a Navier-Stokes fluid. So this is the temperature range we are interested in, where the model more or less works. I'd just like to point out that while the density, the overall density is constant in the whole range, the superfluid fraction, the normal fraction vary a lot, in the sense that already below, let's say, 1.2 Kelvin, the helium is almost entirely superfluid, while at T lambda, the helium is almost entirely composed by normal fluid, and at 1.95 Kelvin, we have almost the same fraction between the two fluids. So I just want to point out something, because here we will be discussing about different superfluids and do a comparison between helium and Bose-Einstein condensate. The big difference is the range of scales, okay? So D is the size of the system, L is the average intervortex spacing, lambda R is the mean free path of the protons, and A naught is the core of the vortex in helium. So you see that there is a span of almost 10 to the 8 orders of magnitude, and between the size of the system and the vortex core. At the same time, there is also a huge ratio between the size of the system and the average intervortex spacing. The green rectangle will be the range of scales we will be interested in. And this is not the case for not the case of BCs, where the ratio is between the size of the system and the vortex core is very small, and the average intervortex spacing is almost equal to the size of the box. Also, very important for the talk of today is that at the level or just below the average intervortex spacing, the normal fluid can be considered the fluid because the mean free path is orders of magnitude smaller than the length scale of the average intervortex spacing. Just the last thing, we see that the ratio of scales is even larger than in classical turbulence in superfluid helium. So we all know what are quantized vortices, but let me just do this slide because the interesting part is at the end. So we know that there are topological defects of the superfluid, that without those vortices, the two components of helium-2 don't speak to each other. They are one-dimensional structures, and one important thing is also that the average radius of curvature is of the order of the average intervortex spacing. We know that the superfluid vorticity is confined to these vortex lines, and therefore the vorticity is actually, to be precise, a delta distribution centered on the vortex lines, around which the circulation is quantized, and hence the velocity, superfluid velocity, is given by the Biot-Savart law. Importantly and fundamental, for this talk at least, is that the vortex line act as scattering centers for the normal fluid excitation. So it means that there's an exchange of momentum, which means that there's a so-called mutual friction force between the vortices and the normal component. And this is proportional to the average velocity difference between the two fluid components, or equivalently, we will see, to the velocity difference between the vortices, the velocity of the vortices, which is indicated with the S dot, and the normal fluid velocity. So this is the first seminal paper by Jovine and Hall, and where he, first of all, he was able to show that the regions where the superfluid vorticity was confined were actually vortex line and non-vortex sheets, because there was also this option. And he also derived an expression for the mutual friction force. And very briefly, we can say that the mutual friction force is composed by two different forces. One is a force which is Fd, which is analogous to the viscous drag, we will see in a minute. So it's proportional and parallel to the velocity difference between the normal fluid and the velocity of the vortex. The second one is the Jordansky force, which was mentioned this morning in Giacomo's talk, and which has to do with the circulation of the normal fluid around the vortex core, and it's perpendicular to the velocity difference between the superfluid vortex and the normal fluid velocity. Then also, because you have a circulation of the superfluid which is quantized around the vortex, then of course you have also a Magnus force, and in order to determine the equation of motion of the vortex, you have to balance the two forces, because as said this morning, especially in helium, the vortex core is empty. So here now let's say that we use classical fluid dynamics. Okay, so this is more or less all the talk will be like this. We have a quantum system, but we will use classical fluid dynamics as long as we can. So to model the what I called FD, so one of the two forces which occurs between the normal fluid and the superfluid vortices, we will use a classical fluid dynamics low Reynolds number approach, borrowing from this approach by Demos Kivotides. We try to go a bit further on, and so this approach is justified by these elements. So first, the force is in fact proportional to the should be Vn minus S dot. So it's like a Stokes drag. The second is that the vortex locally can be assumed like a cylinder. And there is this range of scale separation between the radius of curvature, RC, the discretization on the lines, which is delta, and the vortex core A naught. In addition, the Reynolds number, because of the fact that the vortex core is of the order of the angstrom, and normally the relative velocity is the order of centimeters per second, we have a Reynolds number which is between 10 to the minus 5 and 10 to the minus 4. So what we did is that we applied this low Reynolds number approach, and we modeled the force, what I called FD, so the force which the normal fluid exerts on the superfluid vortices as the force, the viscous force, the drag, which a classical fluid exerts on an infinitely long, thin, solid cylinder. And this, when you do some maths, a bit of maths, you end up that the FD, I'm sorry, here I got FNS, but it should be FD, is proportional to S dot minus Vn, and the proportional constant is given by this this expression where you see that there is this the Reynolds number is in under log in the denominator. So by equating again, as said, the two the three forces actually, Fd, the viscous drag, the Dansky force, and the Magnus force, we get the equation of motion, where beta and beta prime are non-dimensional parameters, and which is, let's say, we always like when those the parameters are actually dependent on non-dimensional quantities. Those two, the ratio of the densities and the ratio between the quantum circulation and the normal fluid viscosity, are temperature dependent, and then the other parameter is the Reynolds number. So this is the messages we used classical fluid dynamics to derive an expression for the viscous drag which the normal fluid exerts on the superfluid vortex. So at the end, what our numerical scheme is as follows. We solve self-consistently the normal fluid velocity by solving the Navier-Stokes equation where there is the mutual friction force is present. There are some issues in how you distribute this force on the grid points, because of course the force is centered on the vortices, and the normal fluid is solved on a grid. And here to do this we use a viscous diffusion model elaborated by Carlo Casciola, Paolo Guartieri, and others in Rome. And then this equation has to be solved self-consistently with the equation of motion of the vortices. Here you can see that, I mean, immediately what pops up is that each vortex element, to calculate the velocity of each vortex element, you have to compute the Biot-Savart integral. So it means that in principle, this is an n-squared problem, where n is the number of segments which you have used to discretize the vortex lines. Of course, you can use some approximation, but it's quite a heavy computation when you want to have a very small resolution, very large resolution, or you have many vortices. Okay, so what are helium-2 counterflows? Helium-2 counterflows are the first systems which were used in, which were studied in a channel, and it was the experiments done in '57 by Weinen where the first time superfluid turbulence term was used. And so what you do to generate is generate it thermically. You place a heater in a closed end of a channel, you switch it on, and then what happens is that you have a temperature difference between the closed end where you have the heater and the other hand. This drives a pressure gradient because of the London equation. And then what happens is that the normal fluid, which is the only component which can carry entropy, hence heat, flows in the other way in order to take heat away. And so therefore the superfluid velocity flows in the other direction in order to preserve mass. Therefore, what we've done by switching on the heater is that we have created an average velocity difference between the two components. And this is a very effective way of transporting heat because it is of convective nature. And in fact, helium is used very much as a coolant in cryogenic application, in fusion prototypes, in CERN, and so on and so forth. The problem is that as long as the two fluids flow laminarly, so the velocity difference is very small, there are no vortices, and the flux is proportional to the gradient of the temperature. But as soon as the vortices nucleate, then the heat flux decreases. So the temperature, the dependence on temperature gradient decreases a lot. And this is because you have these vortices which do some resistance against the flow of the normal fluid. I don't have time to go into detail, but there are many aspects of this helium heat transport that are not, that are not known still, and it's a very interesting subject. So, what does this? What are the consequences of this? The fact that the two fluids move in opposite direction, the fact that there is a dissipation excess, so the spectrum which was measured has a steeper exponent with respect to Kolmogorov. the superfluid, the normal fluid spectrum. The superfluid spectrum is like what you have when you have some random vortices, meaning that you always feel the closest vortex. And then we also have measured some very large turbulent intensity with respect to classical turbulence, in the sense that we also have turbulent intensity of the order of 10 or 20%. Okay, so why we wanted to address this system? So these are the following motivations. So despite the fact that helium-2 counterflows are studied since the late 50s, there's very few information about the fluctuations of the normal fluid velocity. There is a lot more information is needed on the superfluid velocity. We don't need the profile. We don't know what are the profiles in a channel of the superfluid velocity. There are only coarse-grained information on the spatial organization of the vortices in the sense of the vortex line density, so the vortex line length per unit volume. And especially more insight is needed to interpret some ongoing experiments, particle tracking velocimetry experiments, which I think Mathieu will describe on Thursday. And this is because the fact that you have two fluids, so particles interact with all the two fluids, and also because you have, of course, you need to perform experiments at very low temperature. So here are the results. So here, how did we model? So we took a helium counterflow at 1.8 Kelvin with a normal counterflow velocity of 5 millimeters per second. We solved the two-coupled equation for Vn and for the vortices by imposing a mean flow in the two directions. These are the value of the non-dimensional velocities, which would be important for in a minute. So I'll just show you a movie. Okay, this is a movie with just the vortices. You see there are a lot of vortices, but this the important thing, which you can't see here because of the perspective, is that actually the normal fluid, so the vortex lines actually tend to lie on planes which are perpendicular to the counterflow velocity. Then it is probably more interesting to show the same picture with a cut of the normal fluid velocity in the streamwise direction. And you see that the applied mean flow is about here, so it's about when the blue starts. And you see that there are regions where the normal fluid magnitude in the streamwise velocity in the streamwise direction is a lot smaller, where the vortices are present. And then there are areas where the vortices are not there, where the magnitude is larger, because of course the normal fluid must, we have imposed a mean flow for the normal fluid. And this is what you observe. And then something else that we can do is that we can show the same thing with the vorticity in the vertical direction, so coming out from the plane. And you see that where vortices are present, there is vortex dipoles are present. And this is a well-known effect, was shown here in the 20 years ago, that it's like when you have a stick and you move it into the water, you would expect you create two vortex dipoles, okay? So this is the, well, don't show the video, I mean, it's quite obvious. So we went to do something more quantitative, and we computed the PDF of the streamwise velocity, and so the velocity in the direction of the mean flow, and the PDF of the spanwise velocity. And what we observe is that first is that the streamwise velocity is skewed, okay? And the second is that in both cases we have exponential tails, which are for example, are different from classical turbulence. So here this is actually the signature of these regions of velocity where the vortex are, which are decreased because the vortices are moving in the opposite direction of the mean flow, and therefore they are steering the normal fluid velocity, creating a sort of wake. And therefore, this is the reason why you have this skewed PDF. So what we wanted to do is that we wanted to try to find a model a bit of this, of what was going on. So we just took an idealized situation, so a single isolated straight vortices, and we immersed it in a constant flow at infinity of the normal fluid. As said before, we have two forces, the viscous drag and the Jordansky force, so we don't expect, of course, to have a symmetrical pattern because it's not axisymmetric anymore. and we look this at in the frame of reference of the vortex. And so this is what you see for the vorticity. You see the dipoles, which you have seen before in the movie, well, in the snapshot, and so it's fine. Then this is the wake. So this is the magnitude of the velocity in the streamwise direction, and you see that the extension of this structure behind the vortex is a lot larger, corresponding to the vortex dipoles. So if we took instead we look at the streamwise velocity and we do the contour plots, well, what we cannot see here very good, but is that the fact that the wake behind the vortex has a parabolic shape, okay? So we are in presence of a parabolic wake. So what we've seen before, the vortex dipoles and the wake of the normal fluid is described by this simple model of having a lot of many vortices. And actually, if you look at the PDFs of the streamers and the spinal velocity in this simple model, we see that actually we find the same pattern, so skewed for Vx and both in exponential tails. So the idea is that the normal fluid velocity in counterflow helium-2 can be described as a superposition of a uniform flow and two-dimensional flow structure in the sense of vortex dipoles and parabolic wakes, which actually live on planes which always contain the average imposed mean normal fluid velocity, because of course the vortices are on the perpendicular planes to the normal fluid velocity. Actually, so what we are now investigating is how much these structures are different from, for example, what happens in three-dimensional turbulence, classical turbulence, where you have point-like agents which force the flow. In fact, vortices, are effectively one-dimensional structures, so they are lines. Then these wakes are intrinsically have a two-dimensional nature, and also vortices talk to each other. Every line element talks with all the other elements and with a long-range interaction, okay? So the idea would be to explore more in detail, which is the next thing we want to do, and to see if there's some difference with some patterns emerging from active turbulence in classical fluids. So actually, this is not anything surprising, because you can also derive analytically the flow that a moving cylinder, or the opposite, so the flow which the disturbance is created in a viscous fluid by a very thin cylinder. To do this, you have to use the Oseen equation, which is a linearization of the Navier-Stokes equation, which is done by noting that at very large distances, when you decompose the velocity as the flow at infinity plus the perturbation, you can effectively write the nonlinear term like this. So it is actually, so it can be written like this, of course, if it's in the x direction. And it is actually true only at large distances. And in fact, it is used for as a far field correction for the Stokes equation in three-dimensional flow past the sphere. Because in fact, if you don't use the Oseen equation but use the Stokes equation, the flow doesn't go to zero sufficiently fast. But actually, the interesting thing is that in 2 dimensions, the flow past the cylinder, if you use the Stokes equation, you have no solutions. So you have to use the Oseen's equation, which, however, has a drawback. It has a drawback because this decomposition is only valid at large distances, because small v is a perturbation only at large distances. At the boundary of the cylinder, it's equal to minus u infinity. Therefore, it is good only in the first approximation. And if you solve this, you actually see that this is the near field, okay, without going too much into detail. This is exactly the near field which gives you the coefficient for the drag coefficient which you use in the mutual friction force. And you see that there is a dependence of the norm of the Reynolds number. And then this gives rise to the vorticity field like this. So it is effectively in the near field you have a dipole. If you look at the far field solution of the Oseen equation, you effectively have a parabolic wake. So actually, this model of describing what is going on in helium counterflow as a superposition of wakes and dipoles plus the uniform flow seems to work. Also because if you do the PDF of the far region of the wake, you get exponential tails also. Therefore, okay, I spoiled it. So the point is, this is a model. It is the first time that the simulation is made on helium-2 counterflow, but the point is, how this can help, for example, in interpret the experiment. So I won't spoil too much, Mathieu, your talk, But so there are particle tracking velocimeter experiments in helium-2 counterflows where the solid hydrogen particles are tracked and the trajectories are reconstructed. And there, if we look at the particles which are not trapped by vortices, so the one that follow the normal fluid, which are those fast here. So this is the curve. And we look at the PDF of the streamwise velocity, we actually see that this is skewed. So exactly as it is skewed, the one that we observe. However, there is, we are discussing with Mathieu because we have it skewed in the other direction, okay? So this is, now we have to establish who's wrong. I mean, what is the reason for this? But there is an exponential tail in the PDF of the particle. So sorry, I forgot to say, this is the PDF not of the fluid, but the PDF of the particles which we have computed. We have a code which also solves the dynamics of inertial particles. But if you look at the PDF of the velocity in the spanwise direction, well, here probably we could say that there is very good agreement, especially also with other experiments where the experiment shows a v to the -3 power law. And this is due to the existence of the interaction with vortices without being trapped. So probably, I mean, the model that we use today could be of some use in order to describe and interpret the particle velocimeter experiment. So I'm reaching my conclusion. Time, incredible. So we have realized the first self-consistent simulation of helium-2 counterflows. We have observed the PDS with exponential tails and the PDF in the direction, the velocity component parallel to the imposed mean flow are skewed. We have proposed a very simple model for describing the normal fluid velocity in helium-2 counterflows, so superposition of vortex dipoles and parabolic waves, which might help interpreting particle tracking velocimetry experiments. So the perspective is to explore a bit the parameters, because what we have is a lot temperature and velocity and depend on the normal fluid applied average flow. We want to perform more statistics on Vn to compute, for example, a spectrum structure function, even if we have to increase the resolution because we are still limited by 512 cube, which, by the way, for people doing classical turbulence is ridiculous, but I mean, in superfluid helium, till a few years ago, it was 128 cube, so okay, don't be too harsh. We want to study more in detail the particle dynamics in relation with the experimentally, so Mathieu and Marco Lamantia in Prague. Explore also T1, T2 transition, which I didn't have the time to talk about today, which is a region where at certain point the counterflow, there are a lot more vortices when the velocity increases with the power law, which is different. Sorry, with the coefficient which is different. And then coming back to what Giacomo was telling this morning, probably if the mean free path of the excitation in fermions are smaller than the core, then these types of effects at finite temperature could be actually could happen. And for example, if you have very close co-rotating vortices, these dipoles should change the frequency of rotation of the vortices. So thank you for the attention, and I'm here to answer any questions.
Thank you. So I have a question about how does this mutual friction, the way you model it, relate to the microscopic or material parameters, let's say, that Winan introduced? And especially since the Vn now enters into the mutual friction constant, really the D, if I have walls or particles in the wake, will that affect the actual mutual friction interaction? So mutual friction is not a material parameter at all, it's just the drag on a cylinder?
Yeah, so I mean, if I understood correctly the question, so if your particle goes in the wake, this is the question, or if the relation with Winan's coefficients. Well, the relation with Winan's coefficient, the problem with Winan's coefficients, as you know, is that they are determined macroscopically in the coarse graining, okay? So actually, the question would be different. So why, well, probably it was the only thing that could be done in the past, but why for computing the velocity of the vortices at such small scale, which is much smaller than the resolution of Wein's experiment, you use a coefficient which is averaged on many vortices and which doesn't count of the configuration of the vortice and the back reaction with the normal fluid. Second, I mean, I didn't have time to say it, but there are experiments in Florida by Wei Guo, where they have tracked with particles the decay of vortex rings, and they have tried to fit the results with all the different models of mutual friction, and this model is the one that fits the best. Doesn't mean it's correct, but it fits the best than the others. I mean, it's also experimental, independent experimental observation.